exactly the same. So you want to remove any dependence on your interpolating field from the matrix element. So that's exactly what you're taking this ratio here.
So the purpose is, if we know there must be magnetic interaction, the current, the EM current must exist, then how this two-point function will help your calculation?
It's not the two-point function. It's the fact that QCD is a non-perturbative theory, so you don't know how to actually write down the proton wave function, right? All you can do is write down a field that has the same quantum numbers as the proton. But there's some arbitrary number. It could be 10 to the 3, it could be 10 to the minus 7. You have no idea how this actually couples to the proton. And that has nothing to do with the electromagnetic current. So you want to make sure you exactly cancel your arbitrary dependence on your interpolating field onto the state.
But we insert this complete set, we pick up the proton state.
Yeah, yeah. So then what you want is, okay, so just very roughly, what do you have? You have your vacuum, you have your proton, you have your electromagnetic current, proton creation operator. So then you insert 1, sum over n, and you insert 1 here, sum over m. And so then this becomes sum over n and m, vacuum. Sorry, I shouldn't call this the proton. This is some operator with the quantum numbers of the proton. So there's an operator, proton, n electromagnetic current, n operator, dagger, vacuum. So you want this, and you want to cancel that. So this, the dividing out by the two-point function is designed to exactly cancel these pieces. Yeah. Okay, there's one more thing I want to say. Two more things I want to say before turning on the computer. So all we know how to do at the moment is compute elastic form factors, proton to proton, meaning it's an on-shell proton goes to an on-shell proton, meaning if this is pi, this state here satisfies E squared equals pi squared plus m squared. And the final state also satisfies, and when I mean m, I mean the nucleon. Why can't we compute the inelastic structure in the resonance region? Well, so the problem is, say you want to compute the n to delta transition form factor. So this is something I know at least a few people in this room have thought about. The problem is the delta is just a strong resonance of the pi n scattering amplitude. So in order to perform the calculation on the lattice, you have to worry about the fact that what you really have, if you have a proton to begin with, you hit it with a photon, it turns into a neutron pion state. And I was telling you, you can't do scattering with neutrons and pions straightforwardly on the lattice. So that's exactly the problem you have to worry about. You have to worry about how to take this multi-particle state and extract the transition form factor. So the formalism to really understand this just in the last couple of years is being developed. So formally, this is still sort of an open-ended question. If you wanted to rigorously show how to get the arbitrary n to n star transition form factor, you have to worry about multi-particle problem. And so understand, so like I said, what we know how to do now is the two-particle hadron interaction state. But if you put enough energy to have 3 pions, the formalism does not even exist to know how to compute this transition matrix element. And then if you really wanted to compute the inelastic structure, you'd have to perform the calculation for every possible excited state. and then sum them all up to get you the inelastic structure function. Now, that's the one thing I wanted to say. The other thing I wanted to say, which I didn't go into at all, we can, on the lattice, compute moments of the structure functions, which relates to the Parton distribution functions. And you can try to get more clever and compute things related to the transverse momentum-dependent Parton distribution functions. But that would require, each topic alone would require at least a week of full lecture. I could talk to you the whole day about it, and you'd still be puzzling. It's a hard problem. So what I want to do is tell you, you can do it. There's real serious effort in the lattice QCD community around the whole world to try to connect the nucleon structure and really understand these PDFs where possible directly from QCD. So you have perturbative QCD and the asymptotic DIS limit, but you still have this non-perturbative muck. You want to figure out a way to compute that. The only way we know how to compute the soft parts of all these functions is with lattice QCD. But you can still use it to make a connection with all the other speakers have been talking about during the summer school. So what I want to leave you with, actually, is I want to transition to some stuff I've been doing, so this way I can turn on my computer finally. Should I tell you that's all I do with my life, is work on the computer? And I'm going to talk about matrix elements and dark matter in the early universe. So at some point, this will illuminate enough so we can see it. Here's my play button. Okay. So, what do we have? This is just an old picture of the College of William and Mary where I happen to work right now. And I'm sorry you can't read the bottom. I'll put the slides online, so anything you missed that I say that's written down, you'll be able to see it later. Okay. So I want to tell you about dark matter matrix elements. What I'm really going to tell you about is an indirect method to compute these matrix elements. So here, again, I have a matrix element, it's a three-point function. But I told you a few times, what we know how to do better than anything else is spectroscopy. So I'm going to tell you about an indirect method, the Feynman-Hellman theorem from quantum mechanics, it's the same one, to compute these matrix elements using spectroscopy. And then I want to tell you a little bit about how we're connecting QCD to the early universe at a time known as Big Bang nucleosynthesis. Okay, dark matter. We've seen this plot in this talk or the summer school already. Most of the universe is dark energy. We don't know anything about it except that it has to be there. With our current understanding of the expansion of the universe, dark matter. Again, all we know, the difference between dark energy and dark matter is dark energy is relativistic. Dark matter is non-relativistic. We know it's very weakly interacting with itself and with us. As far as we can tell, it only interacts gravitationally. And then the standard model describes the 4% of everything else that's left. Okay, so you can't read it down here, but what I want to tell you is by studying the quark mass dependence of the proton and the neutron, something you would think is boring, why do you care? By studying the quark mass dependence of the proton, you can actually help aid direct dark matter searches, because you can get these dark matter matrix elements. So how does this work? So suppose dark matter couples through the weak sector. So somehow dark matter couples to the Higgs. So the couplings to the W and Z and how they interact with the protons and neutrons have already been ruled out experimentally through all the searches. The only remaining window of hope is through the Higgs portal, as it's called. So if dark matter couples to the Higgs, well, you know the Higgs couples to QQ bar pairs because that's how the quarks get their mass. So that means somehow this Higgs will couple into the nucleon. And if you look at the spin-independent cross-section, then the cross-section scales roughly with the square of this we'll call it matrix element. So this is some number that comes from the charm, bottom, and top quark, as well as the glue. And then there's these U, D, and S matrix elements in the nuclei. And what are they? They're specifically these MQ, Q bar Q matrix elements. So these are scalar currents. So these are, of course, very challenging to measure experimentally, right? We don't have probes that look like scalars, so we can't just simply take a proton, hit it with a scalar current, and see what happens. And then they just happen to be normalized by the nucleon mass. The point is, if it's a spin-independent cross-section, you expect very simplistic arguments tell you would expect roughly an A squared enhancement on a nucleus. So this would be a coherent scattering over the entire nucleus. So it goes like A squared. If you start looking for flavor-dependent couplings, of course, then it depends on protons and neutrons. If you want to look at spin-dependent couplings, you have to worry about most of the nucleus is in a spin-zero state, and you're only coupling to a few of the valence nucleons in this big nucleus. But for the spin-independent cross-section, it's roughly an A squared enhancement, which is why xenon is one of the favorite detectors or chemicals used in the detector. It's a big nucleus. Okay, so it's very difficult to measure this experimentally. You can estimate the light quark, the up and the down contribution from pion nucleon scattering. The strange contribution has been notoriously the most difficult one to estimate. Why? Because trying to include SU3 symmetry into the chiral Lagrangian 4 baryons is quantitatively, it's not, you can't do it really. The chiral perturbation theory, 4 baryons with strange quarks, is not a convergent effective field theory. So you're stuck with large uncertainties at best. So here's a plot showing this quantity F squared as a function of the strange contribution. So here, the up and the down numbers have been taken and frozen from pion nucleon scattering. And then it's plotted as a function of Fs. Only the strange contribution remains. So what is the point? The point is, it's kind of hard to make out. This is an old estimate based on pion nucleon scattering and using SU3 symmetry, which I told you quantitatively does not work. Here's a new estimate that came out a few years ago, coming from the Micro Omega group. It's just a group that produces code to help people who are interested in dark matter phenomenology determine these cross sections of a nucleon. Here's an updated estimate of Fs, again from pion nucleon scattering and SU3 symmetry. The difference between these two numbers is representative of the theoretical uncertainty. And then in this kind of band here is the actual uncertainty from this particular calculation. The point is, if you take this uncertainty, the cross-section has a huge uncertainty. Okay, but we can compute this with lattice QCD. So, yeah.
In the previous slide, you said the 2.9.
Yeah.
Doesn't count the quantum mass. So what's that?
That's like the gluon condensate and the charm bottom top pieces.
Through
The trace anomaly. Yeah. Okay. So I've been talking about how do you compute matrix elements. I just wrote down something that looked like this on the board. We have a nucleon final state, an initial state, and some operator we want to compute. We have the path integral we actually have to perform in our numerical calculation. For example, if you want the nucleon axial current, you would put down this operator. If you want these scalar matrix elements, you put down this other operator. So these are difficult things to compute because of these 3-point functions. There are more complications I didn't go into, but they're just hard to compute. Okay, for the nucleon axial current, in fact, there are no disconnected diagrams at all. Because really you have in here at tau 3, you're taking the difference between proton and neutron to get GA. Or you could put in tau 1 plus I tau 2 and do a neutron to proton transition matrix element, and the symmetries of the theory relate that exactly to the axial coupling of the nucleon GA. So this is a number GA is viewed as a benchmark. You want lattice QCD to be able to reproduce the measured value of GA from neutron beta decay that you measure in an experiment. And there's a sad story about why we haven't been able to do that yet, which I won't tell you, but. Okay. The scalar matrix element, unlike the axial charge, includes both a connected for up and down and a disconnected piece for up, down, and strange. There's no strange valence quarks in the nucleon, so of course that can come from only disconnected contributions. And I told you those are even harder than the connected ones. So here's this new method. It's an old method, newly applied to lattice calculations, the Feynman-Hellman method. If you recall from quantum mechanics, if you have some correction to your Hamiltonian, you can show this all in perturbation theory, so you imagine lambda is small. If you look at how the energy levels vary as a function of this parameter lambda, you can show that's exactly related to the matrix element between the state n and the difference of the, or how the Hamiltonian depends on this operator H1. Okay? So for this scalar quark matrix element, you can take the derivative of the nucleon mass, or the ground state of your two-point function, with respect to the quark mass, multiply it again by the quark mass, and you produce exactly the matrix element you're interested in. Because you know the Lagrangian contains this term, so you can show in the long time limit you recover exactly this Feynman-Hellman theorem, even in the path integral. Why would we multiply by MQ? Well, Q bar Q is not an observable quantity. It's not renormalization group invariant. So it's just much more complicated to compute. If you simply multiply by the quark mass again, because this is an object that appears in the Lagrangian, you know it has to be renormalization, scheme, and scale independent. So whatever renormalization scheme you need to fix Q bar Q, it's exactly the inverse that you need to get MQ. So it exactly cancels and makes your life easy. So then what do? You compute, say, the nucleon mass, and you change the quark masses in your calculation, because in the numerical calculation you're free to dial the quark masses. You compute the nucleon mass, you extract the ground state through the two-point function, and then, so here's an example, if you can make it out, there's some numerical data on here with stochastic uncertainties on them, and you fit the function. This is known as an effective mass. I forgot to tell you what that is, but when this thing goes flat, it means you've reached the ground state. You can perform all sorts of different fits you want. This is just to show that yes, we know how to fit two-point functions very well. You get a nice systematic uncertainty. You can extract the masses very well. Change the quark masses. I wish I could raise my equation up, but I can't. And then you can just numerically construct the derivative. So if you change the quark mass by just a little bit, of course you start approximating the derivative very well. And then this is what you get. So here's a calculation where the strange quark mass was straddling the physical value of the strange quark mass. So you just take the difference and you pick off the slope, that's your derivative. And then multiply back by the strange quark mass. And then we want to stick that back in to this whole picture to help constrain this quantity F, which goes another cross section. So here's an example of a calculation I did myself. Unfortunately, you'll see, let's see, they're both an m pi squared. Anyway, it turns out these pions aren't actually very light. So the calculation I did myself is not that great. But it just shows you how you can extrapolate the calculation from the pion mass you did to the physical value. And you get some value for this strange quark matrix element of the nucleon. So again, my calculation wasn't particularly good. It happens to be this red square here. So these color schemes denote some level of how much you should believe the different calculations, with green being the only one that has sort of rigorously performed all the systematic extrapolations. The yellow numbers are ones that have done a pretty good job or a good job in all the systematic except for maybe one or two. And the red squares are ones where you know at least one systematic has not really been put under control. Okay. But then you can take these things, you can average them, and you get some number. The point is, you'll notice you can't read it, but this is a number that's a little smaller than 0.05. So I've divided by the nucleon mass, so that is something like 40 MeV. Okay? The important thing is, this was the old uncertainty, this value of Fs. Lattice QCD has been used to constrain the value to this much smaller window. So what does that mean? You've taken this large uncertainty in the cross-section and you've put a much tighter constraint on the possible contribution from the strange quark to direct dark matter surges. That's just one way we can use lattice QCD to have a big impact on experimental physics. Okay, I'm already over time, so I won't go into the next part. So everybody needs their coffee. If you're interested, you can ask me later. You can actually do fun things and connect QCD to the early universe, looking at the production of light nuclear elements and how it depends on the neutron-proton mass splitting and tying that into the down quark, up quark mass difference. So it's called, I'm stealing a title from some cool paper written a while ago called Connecting the Quarks and the Cosmos. So thank you for your time. It's been fun. I hope you've had a good time. Learned something about lattice field theory. It's not all very boring. You can do some exciting stuff with it. Okay, thanks.
Any question?
About this NTU-3 baryon chiral perturbation theory, it used to be convergence used to be very bad in the heavy baryon framework, but I remember in some Munich group, it seemed they have published something show the convergence is much better. So, but they only calculate a very few things.
I have strong opinions about what people do.
Okay.
And they're mostly critical.
Okay.
So statement one, all these extra flavors of baryon chiral perturbation theory, on their own, they're not well defined. So they only make sense because they use the power counting of heavy baryon chiral perturbation theory to tell you which graphs to keep. And then, in essence, what they do is so heavy baryon treats the nucleon as a static quark, or sorry, a static baryon. And what they do is they include the full relativistic propagator, so the static one, so the nucleon recoils. So of course that's going to improve a lot of behavior. But by and large, aside from work done in the phenomenology sector where people have looked at polarized abilities, the calculations have been claimed to have better convergence, and they must be better because they compare to lattice QCD data where the pions are so heavy, you wouldn't believe it anyway. It so happens the functions work well. So there's something interesting going on. I don't want to say it's not good work, but I think the claims that of how good it is are overreaching. So the point is, they still need the heavy baryon expansion to have it diagrammatic. You just know which diagrams to keep in the effective expansion. Because if you do the full relativistic thing, you have time derivatives on the nucleon field, which bring down positive power to the nucleon mass. So you lose your power counting. That's why you went to the heavy baryon to begin with. And then it's just simply a different regularization scheme. And so I think you always want to be cautious when one regularization scheme works much better than another. In some cases it's obvious. On-shell renormalized perturbation theory is known to always work better than bare parameter perturbation theory. But this isn't quite the same thing. So in heavy baryon, to get the same correction, all you need to do is include the kinetic recoil of the nucleon. And that will already significantly improve the heavy baryon formula. So I view it as it's a convenient, so what has been shown is these baryon chiral perturbation theories that are relativistic. At one loop, at least it's been shown, it's exactly equivalent in the heavy baryon to re-summing the kinetic correction. And so it's a convenient calculational scheme. And in case we're like, if you're looking at the electromagnetic current hitting the nucleon, like in the polarizability, it is important to worry about the recoil of the nucleon. So I think it's kind of clear in that situation why it's working better. Whereas when compared to lattice QCD, computing the static mass of the nucleon and saying, oh, as I make the quark mass heavier, this formula has a better convergence. Well, first of all, in the, sorry to rant, in the baryon, the relativistic baryon theory, you have to keep the full spin of the nucleon. And to date, no one has really kept also the delta. I think Vladimir is working on that, if I remember. But if you look at the heavy baryon expansion with and without a delta, if you just throw the delta degree of freedom away as a dynamic degree of freedom, the convergence goes back to what people are getting with the relativistic baryon chi-bt. So the convergence is not a matter of the relativistic formulation versus heavy baryon, it's did you include the delta degree of freedom or not? So I think the literature is very muddled and people are making much stronger claims than they should.
Actually, my thesis is about how the delta is kind of heavy baryon kind of perturbation, but my dimension is catching on 5 is time.
Well, they're not including the delta again. I have a strong opinion. This doesn't make sense. It's a dynamic degree of freedom that's light. You're gonna resonate this thing.
Sure.
If you try to just include it by saturating the low energy constants, it's not gonna get all the physics right. And of course, if you make the pion sufficiently heavy that the delta is stable, then you have no justification not to include it. If you use large NC power counting, you have no justification not to. But in the large NC limit, the proton and the delta become degenerate. You have a rigorous field theoretic way to include both. The unstable nature of the delta comes from higher order NC corrections. Sorry, I could rant for hours about all this.
The Feynman-Hellman theorem provides a good way to deal with the scanning diagrams. So it seems one can generalize this to arbitrary arbitrary kind of source and current, which is actually to the source. Does anybody deal with that?
I'm working on that right now. Yeah, I think so.
So your arguments, main motivations, you are doing this calculation in order to constrain couplings of Higgs to dark matter. And so you showed cross-section proportion to this F squared. So proportionality, of course, is something we want to extract from somewhere. And so you will have some limits which you can exclude. So people have done this in the case of this so-called light dark matter, because in this case this hypothetical particle will couple to leptons, and then you can directly measure in the lab. But which experiments are really being done, and what are there already exclusion limits which are being shown or something?
Yes, I don't have it on my computer. The situation is very depressing with the latest LUX results. The LUX detector has killed almost all, I mean, it's very tight constraints on dark matter. Of course, what we don't know is, I have it here, and I went too far. We don't know this side, whatever the how that's coupling. And so just knowing this part helps put that constraint up there. I don't know the number off the top of my head, but people are starting to really seriously think about spin-dependent couplings and flavor-dependent couplings, because my understanding is the latest results from LUX have put such tight constraints on anything that's above, I don't know, HL squared, that there seems to be nothing there. So LUX came in and it ruled out the, I'm blanking on the name, the germanium detector that was just used to find, or was it silicon?
Super CDMS?
CDMS. So CDMS found 3 potential signals for a light dark matter particle.